let's go ahead and start. So we have Unit 7. This is going to be into two different parts. We have Part A, which is going to be thermochemistry, kind of a review from last year or year before last. And then thermodynamics, which will happen in the next Part B. So first of all, energy. You've learned about energy throughout your education. Hold on, I'm trying to get back to where I was. Okay, so energy is the capacity to do work. You need to know that the law of conservation of energy, that is our first law of thermodynamics, where energy cannot be created, can be converted from one form to another, but cannot be created nor destroyed. So the total energy in the universe is constant, and we call this delta H, and that is our enthalpy. We'll get more into that in the next part B. But total energy, which is delta H, and that's our enthalpy, is constant. Potential energy, kinetic energy, you should know that. Have y'all done this in physics? You guys have already gone through physics. No, what about just thermo? Have y'all done thermo? No?
You do that in
Physics too. Okay. So then next, heat is involved with the transfer of energy between two objects, and then you need to know that work is a force acting over a distance. Energy is a state function, and what do I mean by a state function? That is, it doesn't matter how we get there. It just depends on the present state. So for what we're going to talk about, enthalpy and entropy and Gibbs free energy, we can solve for those a lot of different ways, but it doesn't matter how we get there as long as we kind of get there, okay? We still end up where we need to go. So here, if I live here and here's the high school, I can leave the high school and go to Walmart, and then after Walmart I can go to H-E-B and then wherever, and then go back to the high school and then go home. But in the end, I went from the high school to home. All right? That is a state function. Okay. So, what you need to know about this is that there is the system and there is the surroundings. In chemistry, the system is going to be where the reaction is taking place. Okay, that is our system, is the reaction. And surroundings is going to be everything else. There are two different types of reactions. There's the endothermic, where heat flows into a system. So if I have delta H and I'm flowing into it, then delta H is going to be a positive number. And think of endo as enter. Okay, endo, enter, entering into the system. In an exothermic system, we have a delta H, and this time it is going to be negative because it is leaving. So exothermic, and exit, exiting the system. But all in all, what is gained has to be equal, or what is lost has to be equal to what is gained, or vice versa. Any questions on that? Okay. So potential energy diagrams, you should have seen these last year. We have, say, here's a potential energy, our initial state. And then if it goes like that, our potential energy, what is happening to our energy? Our energy is leaving the system, right? And so this is what type of diagram? Exothermic. And then if you have your other one, this, we're putting energy in, so this is going to be endothermic. We added energy. So you should be able to recognize those two types of graphs. Everybody good with that? Okay. So, next. Is the freezing of water endothermic or exothermic? Freezing of water. So water does what? Water goes from being a liquid to a solid. So what happens to that energy? It's going down, so energy decreases. So energy is going out, so it is an exothermic process. Everybody good with that? Okay. Now let's classify these as exo or endothermic. The system is underlined in each sample. So our system, your hand, gets cold when you touch ice. So what type of process is going on? Endo or exothermic? Exothermic. Oops. All right. Now this time the ice is the system and it gets warmer when you touch it. So that is going to be an endothermic reaction. What about when water boils in a kettle being heated on a stove? So water boils, so we're going from a liquid to a, oh wait. Water boils. So this is making, so is heat added or leaving? It's added, so it's going to be an endothermic process. Water vapor condenses on a cold pipe. So we're going to be exothermic, and ice cream melting is what type of process? Going from a solid to a liquid, so that means it's going to be an endothermic. Any questions on that? All right. So in this one, for each of the following, define a system and its surroundings and give the direction of energy transfer. So methane is burning in a Bunsen burner in a laboratory. So what is the system? What is the surroundings? Methane's the system, and that means that the Bunsen burner is the surroundings, or the laboratory. But what's providing the burning? The burning is coming from the Bunsen burner.
Well, what if the laboratory was set to a specific?
Okay. whatever. So what type of reaction is this? Exo or endothermic? It's burning. So I have that it is exothermic. So we have this combustion. What in combustion, what do you give off? You give off oxygen and heat. So this is going to be exothermic. And this time, water drops sitting on your skin after swimming evaporate. What's the system? Water drops. Your skin is the surroundings, and the water drops are evaporating. So it is going to be endothermic. Questions? Okay. So thermodynamics is the study of energy and its inner conversions. The law of conservation of energy is often called the first law of thermodynamics. We talked about that. There are two things you need to know about these quantities from thermodynamics, and one is the number. It gives us the magnitude of change. And then the thing that you need is the sign. The sign is going to indicate the direction of the flow. So there are no, you have to have a sign. If it says that 200 joules was released, then don't tell me 200 joules. You got to tell me that that is negative 200 joules. If you don't put a number there, I'm going to assume you mean it's or a sign there. I'm going to assume you mean it's positive. Okay. So, and then internal energy is the sum of the kinetic and the potential energies together. And to change the internal energy of a system, what we do is we have the delta E, the change in energy, is equal to Q, which is heat, and W, plus W, which is work. Okay, so Q is our heat, and the change in energy is going to be Q plus W, our heat plus our work. So you just need to, I don't think that equation is on your sheet, so I would make sure you know what delta E in an internal energy is. Okay, so a sign reflects the system's point of view. So endothermic process, Q is positive. So we know in endothermic, Q, which is our what we've been calling energy, is positive. Okay, so Q for now on is equal to heat. In thermo or in AP physics, I think you guys use capital Q. We use little q in here. And Q, if Q is negative, then it's an exothermic process. Okay, so endothermic, positive Q, exothermic, negative, which that should be reviewed from pre-AP, except for we didn't call it Q then. And then next is, oh, that was an extra slide. Next one is the system. So you need to know what happens to W. So if system is doing work on the surroundings, okay, so if I have a test tube here and I have, say, magnesium and hydrochloric acid in it, and when I add those together, it's going to produce a gas, right? And so if I have a balloon here, then what we would see happen during this reaction is that balloon's going to inflate. Okay? So if that balloon is inflating, then that means the system is doing work on the surroundings. So that means W is going to be negative. So work is negative. So if you think of it this way, you are the system, and I tell you to go mow the lawn in 105-degree weather, what is your reaction going to be? No. Your reaction is going to be negative. So that's how to remember that. Yes?
So exothermic has negative.
We're going to have to look at that and see. It can be different. All right? So you just need to know what Q is and then what W is. Is your W negative or positive? So then if I ask you to do work and you tell me no, then that's a negative work. But if, say, I don't know, you went to the spa, you're still the system, but you went to the spa and you got a pedicure and a manicure and you're being all pampered, now your surroundings is doing work, all right? And so then that's a positive experience. So you doing the work is negative if you're the system, and then if you're the system and work is being done towards you, then it is positive. Okay? So here is a system composed of a gas and flexible container. If the gas expands and then it pushes this out and it is doing work in the atmosphere. If it's compressed, then it is having work done on it, and then therefore the sign would be positive. Okay? So, work, here's your equation. Work is equal to negative pressure times your change in volume. So P is pressure, and delta V is the volume of your final minus your volume of initial. When we talk about work, we talk about it in joules, but when you have negative P times delta V, you get liters times atmospheres. So you might have to convert from liter atmospheres to joules. And for every 1 liter atmosphere, it is equal to 101.3 joules. And I think that is on your reference sheet somewhere. I don't know. I don't see it up there. Any questions on that conversion? So now we're going to do some problems. So you need your calculators, maybe, unless you can do it in your head. All right. So which of the following performs more work? All right, so what is our equation for work? Work is equal to negative P delta V. So a gas expanding against a pressure of 2 atmospheres. So work is equal to negative 2 times going from 4 to 1. So what is work in that problem? Negative 6. Now, a gas expanding against a pressure of 3 atmospheres. So now work is equal to negative 3 times 3 minus 1. So work this time is negative 6 LATMs. So who is doing more work? Neither. They are the same. Any questions on on that? All right. So next, and this comes to Lauren's question a while ago. Determine the sign of delta E for each of the following with the listed conditions. Well, what's the formula for delta E? Delta E is equal to Q plus W. Okay? So that's the equation we're going to look at. We're going to look at this without numbers. So an endothermic process. So endothermic, what is our Q? Positive or negative? If it's endothermic, then it's a positive Q. And it performs, so we have a positive Q, and it performs work. So is our work positive or negative? If you're asking the system to perform work, negative. Okay, so this is the equation we're looking at. So if work is greater than heat, if this number is bigger than Q, then what can we say about this? Is it the answer going to be negative or positive? It's going to be negative. If our work is less than, if this number is smaller than Q, then what can we say about this process? What would our magnitude, our sign be? Our sign would be positive. Again, this next time, if we do work is done on a gas, so that means that we have a positive W, and the process is exothermic, that means that is negative Q. If the work number is greater than heat, greater than Q, then what is our value going to be? Our sign should be positive. And vice versa, if now heat is greater than work, then we should have a negative sign. Everybody okay with that? Okay, so we're going to do a couple of these problems and then we're done. Oh no.
What is Big Mama?
Oh, you'll have to find out tomorrow.
Oh, you'll know. Oh, you'll know what Big Mama is.
We have Big Daddy. Now it's time to have Big Mama. All right, calculate delta E for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. So delta E is equal to Q plus W. It's endothermic, so we know it's going to be positive 15.6 kilojoules plus work is being done on the system, so that's going to be a positive. So that's going to be plus 1.4 kilojoules. So what is our delta E? 17.0 kilojoules. We go to our sig figs, we're adding, so we go 1 decimal place. All right, next, calculate the work associated. So we want to figure out work this time, and we know that work is equal to negative P delta V. With the expansion of a gas, so the expansion of a gas means that the system is doing the work. Okay, so if we have an expansion of gas, that means system is doing the work. And we go from 46 liters to 64 liters at a constant external pressure of 15 atmospheres. So if we know system's doing the work, then our answer here better be negative. All right, so negative, our pressure is 15. And our delta V is going to be 64 minus 46. And that gives us an answer of what for our work? Negative 270, and our unit is liters times atmospheres, latums. Now, if it would have said what is the calculate the work in joules, then we would have converted this to joules, but it did not ask us to do that, so I'm okay leaving it there. Everybody good? One last problem? All right, and a balloon is being inflated to its full extent by heating the air inside it. In its final stages of process, the volume of the balloon changes from 4.00 times 10 to the 6 liters to 4.50 times 10 to the 6 liters. By the addition of 1.3 times 10 to the 8 joules of energy as heat. Assuming the balloon expands against a constant pressure of 1 atmosphere, calculate the delta E for the process. So my overall goal is solving for delta E, right? And delta E is equal to Q, my heat, plus my work. So how much heat do we have? How much energy are we giving it? We are giving it 1.3 times 10 to the 8th joules of energy. What is our work? Well, we don't know what the work is. It hasn't told us, but we can figure out the work because we know the pressure. So work is equal to negative P delta V. So if the balloon is expanding against a constant pressure, so the balloon's getting bigger, which means then therefore the system is doing the work. So that means our work better be a negative number. Okay, so negative, our pressure is 1 atmosphere, and our delta V is what is it? 0.5 times 10 to the 6 liters. And that tells me that my work is negative 5 times 10 to the minus 5 liter atmospheres.
How did you get to the minus 5?
Oh, not minus 5, sorry, positive 5.
How did you get 5?
Because I just moved my decimal over.
Oh,
Because it was 6.
Oh, yeah.
All right, so this is W, right? So now I take W and I plug it into delta E. So put that in equation in there and tell me what is the answer for delta E.
Don't we have to convert the...
Oh, yeah, we do have to convert. So now we have negative 5 times 10 to the 5th latums. And for every 1 latum, there are 101.3 joules. I have this right here on my paper too. So that means I get negative 5.06 times 10 to the 7th joules. And that is what's plugged in to our energy. Add those two together, you get 7.94. We're adding, so it should be just one decimal place, so 7.9 times 10 to the 7th joules. Everybody good with that? So, your homework for tonight is 7A. There's 8 problems. And that's it.
Hey, Marcus.